Alright everybody, so we are just about ready to answer that first big question from the course, which was how do we find the slope of a tangent line to a curve? To answer that question, we're going to develop something called the derivative, and we are one step away from actually being able to define derivative. First, what we're going to do is we're going to talk about something called average rate of change. And you might say, well, what is the average rate of change? It's a general idea to get a kind of sense of how a function is behaving over a given region. So for instance, if you're talking about like a fighter jet diving, right? You're saying F4 fighter jet diving at a 45-degree angle at 800 miles an hour or whatever speed it would go at, you implicitly understand that it's not 45 degrees the whole time it's diving, and it's not going at precisely 800 miles an hour the whole time it's diving, right? Because of air resistance. Or if I say, oh yeah, I was going 60 on the 405, not that you would ever get up to 60 miles an hour on the 405 freeway. It is known as San Diego's greatest parking lot. But assuming you did, you implicitly understand, okay, I'm not going exactly 60 miles an hour my whole time. It's just an average idea. And average rate of change is going to give us that same kind of information. So, definition, the average rate of change and this is a little different than your book's definition, but it's the one we're going to prefer. The average rate of change of the function f of x between x equals a and x equals b. So we're talking about how the function is changing between a and b, right? So on a given region, how is the function changing? And it's defined as the average rate of change, which I'm just going to abbreviate from now on as AROC, is equal to f of b minus f of a over b minus a. And this might look kind of familiar to you. Change in y over change in x. So this looks awfully like the equation for a slope of a line. And that's actually exactly what is going on. If we graph a function f, and let's say a is here and b is here, we have this point and this point. So we have our point a, f of a, and our point b, f of b. And what the average rate of change is saying is, okay, to find it, I want you to take f of b minus f of a over b minus a. That would be exactly the slope of the line passing between those 2 points. This is known as a secant line. So let's do a couple examples of computing average rate of change, and then we'll see how that connects to the derivative. All right. You know what? Let's just do one example, but it'll be a fun one. How's that for a change? All right, so 2 years ago, there was kind of a overpopulation problem for moose. I'm going to go ahead and use the word meese. I know it's incorrect, but we're going with it anyways. For the meese in Michigan. And so, they being local wildlife population controllers in the area, airdropped some Canadian wolves into Michigan. To deal with moose overpopulation. I am, in fact, not making this up. Yeah, people come up with the darndest ideas. In fact, this isn't the first time that something like this has happened. Way back, I think about like 50 years ago or so, there was a plague of rats, essentially, on some island. And the rats had like some disease, they were running around doing their thing. And some bright spark at the World Health Organization was like, you know what we'll do to solve this problem? We're going to airdrop cats in. And the kind of even more disappointing part is that actually worked. So yeah, a long tradition of people airdropping animals in to deal with other animals. Yeah, if I tried to draw a picture, it's going to be absolutely terrible since my art skills are not great at the best of times, but we'll try it anyways. So we got our wolf. If you skip this part of the video, I'm not going to be upset. So we have our wolf, and then below is our moose, and he's very, very upset that the wolves are being airdropped into him and his family. Anyways, that's a long side tangent to set up this problem, which actually does deal with average rate of change. How, you might ask? Well, as the wolves drop from the plane, because of how gravity works really close to the surface, it's actually well modeled by a quadratic equation. So, the distance they have fallen after t seconds is well approximated by d of t equal to 16t squared. If you've taken an introductory physics course, that might look familiar. But yeah, so the distance they have fallen after t seconds is d of t equal to 16t squared. Let's find, there goes my nice chalk. Goodness gracious. I need to stretch more before doing these classes. Okay, so let's find some average rates of change. What would an average rate of change represent here? Well, an average rate of change is their average speed while falling. Okay, so let's compute the average rate of change for a couple different intervals. So let's compute the average rate of change between A, t equals 2 seconds, and t equals 4 seconds, B, t equals 3 seconds, and t equals 4 seconds. Yeah, I know. Fun picture, but it's going away. And then let's do one more part for this. Let's say between t is equal to A and t is equal to a plus h. And we'll care most about this last example, and we'll see why in a second. So, to compute, let's do part A. According to our formula, the average rate of change will be d of 4 minus d of 2 over 4 minus 2, right? Between 2 and 4, we take we evaluate the function at our second point, subtract the evaluation of the function at the first point, and divide by the distance between the points, right? So d of 4 minus d of 2 over 4 minus 2. Start computing. Plugging in 4 to that function there gives you 16 times 16 minus 16 times 4 over 4 minus 2, aka 256 minus 64 over 2, which is 252 minus 60 is 192 over 2, which is 96. And this would be in terms of feet per second. So we know that on average, between 2 seconds and 4 seconds, the wolf's speed was 96 feet per second. Great. Let's do part B. I'll step out of the way so you guys can look at that for a second. Alright, let's do B. I'll reuse this same space so I don't have to erase the problem statement. Yeah, I'm just going to grab a better piece of chalk. Alright. Also, I know, it's a little weird when I just sometimes go off camera. Them's the breaks. Okay, part B. We now want the average rate of change between 3 seconds and 4 seconds. So it's going to be the same kind of idea. The average rate of change is going to be now d of 4 minus d of 3, since we're using 3 as our starting point, over 4 minus 3. This is 16 times 16 minus 16 times 9, right? 3 squared is 9. Divided by 4 minus 3 is 1. So we're left with 256 minus 16 times 9 is 90 plus 54, 144. Okay? 256 minus 144 is 56 minus 44. That is 16 minus 4, 12. Sorry, not 12. 112 feet per second. I was like, that should not be slow. Okay, so on average, between 3 seconds and 4 seconds, the wolves were falling at 112 feet per second. So we can make a kind of reasonable guess that, they were actually traveling slower between 2 and 3 seconds than that 96 number. They're traveling faster than in between 3 and 4, we've calculated here, and that computed to give us our part A reasoning of 96. Alright, let's do part C, since part C is the actually most relevant one for this course. Okay, here we have A and A plus H. Let's not think about it for now, let's just compute and see what we get. According to our formula, the average rate of change will be d of A plus H minus d of A over A plus H minus A. Okay, plugging these into our formula for d of t, we get 16 times A plus H squared minus 16 A squared over a plus h minus a. Expanding a plus h squared out, this gives you 16a squared plus 32a times h plus 16h squared. I also distributed the 16 in there. Minus 16a squared all over a plus h minus a. Merging like terms in the numerator, the 16a squareds cancel out, and we're left with 32ah plus 16h squared divided by just h on the bottom. Okay, h's can cancel out, and we're left with 32a plus 16h. Okay, so let's think about why we did that last example. Why does working with a variable time give us any sort of information? Well, we can always express a difference in times as time 1 and time 1 plus something. And that's exactly what's going on here. We're saying, hey, start at a seconds whenever a might be, it's any number. And then our second time, we're going to say is a plus some amount of seconds, h, right? And here, what we've computed is now, between a and a plus h, the actual average rate of change will be 32a plus 16h. So if we check that with our result from a, maybe, right, a was supposed to be 96 feet per second. Here, a would be 2, and h would also be 2, since 4 minus 2 is 2. And we would get 32 times 2, 64, plus 16 times 3, which is 48. Yes, 64 plus 48. That's right, it's not times 3, it's times 2. So, going up to here, a equals 2 and h equals 2. My bad, I was computing with a equals 2 and h equals 3, and that would be wrong. So, in this case, we get 64 plus 32, and that does give us our 96 as desired. If we tried it with part B, in this case, a would be 3, and h would be 1, since there's a delta of 1 between our two times. And we get 32 times 3, which is 96, plus 16, and that does, in fact, give us 112. Which is what it should have been all along, is 112 feet per second. So we see that this formula does hold for our previous two examples. But why is this relevant to calculus? How does this help us answer our tangent line problem? For that, let's draw a picture. Alright. Let's say we have a function that looks like this. And I wanted to find the tangent line to our function at this point. So maybe this is our a. And I'm trying to find the slope of this line. We ask ourselves, okay, how do we get there? Well, let's start taking some average rates of change. Maybe this is a plus h1 right here. Okay, the average rate of change between a and h1, a plus h1, would give us the slope of that red line. Okay, great, but still not what we want. What about a plus h2 in between there? Okay, well the average rate of change between a and a plus h2 would give us the slope of this line right here, which is much, much closer to our original tangent line. Let's pick one more point. And let's say that this is a plus h sub 3. The average rate of change between those two will give us the slope of that line. And we see that the lines are getting really, really close to our original tangent line. So now, by measuring averages, we're getting really, really close to approximating instantaneous information that's only relying on one point instead of two. And that's exactly what we want. Now, is there any way that we can mathematically quantify this process of getting closer? But that's what we've been doing this whole time, right? We've been taking limits. So, let's set up this equation using an arbitrary function, f. New definition. This is the most important definition for the first half of the course. You know what? It's important enough that I'll write it up there instead. All right. The derivative of a function f at a point A which we will denote as f prime of A. So it's f with a little tick mark, accent mark, and we read it as f prime of A is given by the following formula. F prime of A is the limit as h goes to 0 of f of A plus h minus f of A divided by h. And let's just recall here that h is the same as A plus h minus A. Okay, so this is our definition of derivative, and we see that this is saying, hey, take average rates of change as h gets smaller and smaller and smaller. And if you take the limit as it goes to 0, right, so eventually h goes all the way to 0, then you have what's known as the derivative of the function at A. And this is precisely the slope of the tangent line to the graph at A. Now, it's just the slope, it's not the full equation for the line, right? You need a slope and a point on the line to get the equation. Thankfully, you have a point on the line, so you can find an equation for the line instantaneously after taking the derivative, but f prime of A does not have that information by itself. It's just the slope. So, f prime is the slope of the tangent line. For those of you who haven't heard what a tangent line is before, because I keep tossing that term around, a tangent line is a line that hits a curve at only one point. So, tangent line to the graph of f at the point a f of a. It is also the instantaneous rate of change. Of f at a. Alright, so why is this instantaneous rate of change thing important? Well, I'll give one just quick example from the top of my head. Maybe the speedometer of your car, right? The speedometer of your car wouldn't be very useful if it could only tell you what speed you were traveling after you've already traveled past that, right? Or if it's like, well, on average you're going this much. That's not helpful. You look at your speedometer to know if that cop is going to pull you over right now and how good you need to be preparing your excuse. As you can imagine, I'm a Southern California guy, born and bred. Speeding is kind of in my nature. So, I need to know what speed I'm at right now, and the speedometer gives you that kind of information. So, similarly, the instantaneous information that a derivative gives you, this instantaneous rate of change, is really important. Or say you're talking about a business and you're looking at how costs are going up, and you need to know at this point in time how costs were changing. Derivatives are your tool for finding information like that. Okay, so this is a derivative at a point, but we can also talk about a derivative as a function. And by that I mean, well, okay, a is a fixed point, but what if I let a just be anywhere on this curve, right? What if I let a be a variable? So, definition, the derivative of a function f. So, subtle thing, this is derivative of a function f at a point a. This will just be the derivative of a function f. Is f prime of x. And the only difference between the definition of derivative at a point and definition of a derivative as a function is we're using x instead of a. It's the limit as h goes to 0 of f of x plus h minus f of x all divided by h. Alright, so that's the derivative of the function, and what this is saying is this encodes the information of the derivative at the point everywhere that a could possibly be. And whenever we define a new function, we need to talk about its domain. The domain of f prime is the set of all x where that limit exists, right? We've shown in our previous videos that limits do not necessarily always exist, but whenever this one does, well, we want to be able to evaluate it. So we're going to say that the domain of the derivative function is wherever the limit exists. Alright, we actually have a few different ways to write the derivative in terms of notation. Alright, so we can write f prime of x, or we can write d sub x of f of x. This little sub x just lets us know what variable we're taking the derivative with respect to in what's known as multivariable calculus. If you have a function depending on multiple things at once, you can talk about, oh, the derivative with respect to this, derivative with respect to that, because the function might be changing in different ways with respect to its different inputs. But we won't worry about that. None of you who end up not taking Calc 4 will worry about that. So, d sub x of f of x. Also, if we write like y is equal to f of x, so think like y equals x squared plus 4. We also can write that f prime of x is equal to dy over dx. Please note, this is not a fraction, it's a formal symbol. You cannot separate these two things from each other. You can also write it as just y prime. Different notations are useful in different contexts. These ones are nice and quick to write, don't take up a lot of space, but this one can be more useful depending on the actual problem at hand. We'll use it later on when defining things like the chain rule. Yeah, this is the Leibniz notation. This is really close to Newton's notation. He actually used dots, so he would put like y dot. As for the reason we don't use y dot, and I won't even put it on this list, that's because that's what the physicists and the engineers use. We are not physicists and engineers. We are in a math class, and we have our pride. It's all we have because they get paid more than us, but we have our pride. Okay, so the question becomes, how do we compute a derivative? So to compute a derivative, using the limit definition, so using this definition here, if this was all we had to work with. 3 steps. First, we're going to compute f of x plus h. Just find that thing right there. Second, you'll compute f of x plus h minus f of x. Okay, all well and good, right? You're just computing the numerator. And finally, you'll evaluate the limit. So compute the limit as h goes to 0 of f of x plus h minus f of x over h. And that is f prime of x. So let's do a couple examples. Let's let f of x equal to x plus 1. And we're going to find f prime of x using this limit definition of the derivative. Okay, so step 1, let's compute f of x plus h. Well, f of x plus h is just plugging in x plus h for x. So this is 2 times x plus h plus 1, aka 2x plus 2h plus 1. Okay, subtracting f of x from that, we have 2x plus 2h plus 1 minus 2x plus 1. Which is equal to, okay, the 2x's cancel, and the 1's will cancel, and we're left with just 2 times h. Now let's evaluate our limit. Limit as h goes to 0 of f of x plus h minus f of x, aka 2h, all divided by h. So this is the limit as h goes to 0 of 2h over h, and I'm receiving a call. I'll be right back. Alright, I'm back. Hopefully I can remember where I was. I think I was computing the limit. Yes. So, limit as h goes to 0 of 2h over h, h's cancel. This is the limit as h goes to 0 of 2. Limit of a constant is just the thing. So this is 2. Therefore, f prime of x is just the constant function 2. How about that? Okay, let's do another one. let's let f of x equal x squared minus 2. And same drill, we're going to want to find f prime of x. Find the derivative with respect to x. Okay, so let us compute this using our method. F of x plus h is x plus h squared minus 2. Expanding that out gives us x squared plus 2x times h plus h squared plus 2. All right, great. Now let's do the second step. F of x plus h minus f of x. Okay, x squared is going to cancel out. This should be minus 2 here. My bad. The x squared is going to cancel out, the minus 2 is going to cancel out, and we're left with 2xh plus h squared. Great. And now, the limit, as h goes to 0, of f of x plus h minus f of x over h is equal to the limit, as h goes to 0, of 2xh plus h squared divided by h. Nice, we have an h with both terms on the top. So we can cancel out and we're left with the limit as h goes to 0 of 2x plus h. Okay, well 2x is constant with respect to h, right? There's no h's in this part, so that part's going to do just fine on its own. And this part goes to 0. Using our limit laws, I guess we can explicitly say this is limit as h goes to 0 of 2x plus limit as h goes to 0 of h, which is just 2x, since h goes to 0 as h goes to 0. All right, and that's our derivative. F prime of x, in this case, is 2x. How about that? Let's do one more example using the limit definition. Let's let f of x equal negative 1 over 2x. Now let's do a two-part thing. Let's find f prime of x and answer the question, what is the slope of the tangent line to the graph of f at x equals 3. So in this case, we're actually looking for f prime of 3. Okay? Well, same old drill. We start by computing f of x plus h. That's negative 1 over 2 times x plus h, aka negative 1 over 2x plus 2h. Now we need to subtract. F of x plus h minus f of x equals 1 over 2x plus 2h minus 1 over 2x. Let's get ourselves a common denominator. This is x over 2x squared plus 2h times x. So I multiplied the top and bottom by x here. Minus h plus x. Sorry, yeah, x plus h divided by 2x squared plus 2hx. So I multiplied top and bottom by x plus h right here. Now these have a common denominator, and we can subtract. This gives us x minus x cancels, negative h over 2x squared plus 2hx. Now, there's one crucial thing that is wrong here. Namely, I dropped a negative sign. This should be negative, this should be positive, this should be negative, this should be positive, and therefore this should also be positive. That's on me. Okay, so we have h over 2x squared plus 2hx. Now let's take our limit. Erasing this example in here. This is the limit as h goes to 0 of f of x plus h minus f of x over h. You might ask yourself, okay, why didn't we just compute the limit here? Right? That would have seemed way easier rather than going through this whole process. Well, that's the thing. If you tried to compute the limit without going through this process here, it would get ridiculously nasty. So it's always best to simplify fully in both of these steps before you move on to calculating the limit. Okay, now computing this limit gives us that the limit as h goes to 0 of h over 2x squared plus 2hx divided by h, excuse me. Alright, we take that and simplify using our fraction laws. This is the limit as h goes to 0 of 1 divided by 2x squared plus 2hx. Using our limit laws, this is the limit as h goes to 0 of 1 over the limit as h goes to 0 of 2x squared plus 2hx. You would use your limit laws, split that on the bottom. You get 1 divided by, okay, plugging in 0 for h, 2x squared. And that's our derivative. So f prime of x would be 1 over 2x squared. Now we need our question. What is the slope of the tangent line to the graph at x equals 3? Yeah, let's put that over here. That slope is merely evaluating the derivative at x equals 3. We want f prime of 3. Okay, well, what's f prime of 3? Just plug in 3 to f prime of x, and you'll get 1 over 2 times 9, so 1/18. Derivative as a function is a function, obviously. And then the derivative at a point is a number. All right. Now, you might ask yourself the question, are all functions differentiable? And unfortunately, the answer is no. This limit does not necessarily always exist. And there's a couple easy to see examples of that because they have pictures. Perhaps the most simple function where a derivative does not exist would be the absolute value of x. So let f of x equal the absolute value of x. F prime of x does not exist. Why? Well, let's graph the absolute value of x. Specifically, f prime of 0 does not exist. You can define f prime of x elsewhere. So I guess this is probably misleading to say is that f prime of x doesn't exist. F prime of 0 doesn't exist. And the domain the set of all real numbers not equal to 0. So, I suppose I misled you to start. F prime of x exists, it's just that its domain cannot have this corner point. And we ask ourselves why. Well, okay, any point here, or here maybe, those all work just fine. Out here, something like that, slope of the tangent line makes sense right there. So the derivative exists there. But f prime of 0 doesn't make sense. Why? Because there's no way to choose. Should that tangent line be that thing right there in purple? Or should it be this one in blue? I don't know. So there's no way to choose what happens to absolute value at that corner point. Therefore, the derivative doesn't exist there. The slope jumps. And as we know, when there's a sudden jump, limits fail to exist. All right, what are some other examples where the derivative doesn't exist? Let's draw some pictures to see. I'll be more specific. These are functions where the derivative doesn't exist at a single point. Maybe we have a function that does something like that. And let's call that point A. This is maybe function g. G prime of A does not exist. Everywhere else works, not that corner point. Corners are basically the thing that causes problems for derivative. There's one other important thing that causes problems. Let's do another example with a corner. Something like that. Derivative won't exist there. So this is h, and this is b. H prime of b doesn't exist. The only other thing that can possibly cause a problem for derivative is if the tangent line is vertical, because then its slope is undefined. So maybe you have something that looks like that. And right there, right at the point where the tangent line is vertical, the derivative doesn't exist. Because again, the slope of the vertical line is undefined. Now, there are places, certain functions, that are not differentiable anywhere at all. Those are really nasty. We won't deal with them in this course, but they're quick enough to draw that I'll give you a picture. One of them is a function that is discontinuous, right? Anywhere that there's a discontinuity, derivatives will not exist. So maybe a function that looks just like this. And it's a bunch of scattered dots, so on and so forth. The typical choice is maybe f of x, which is -1 on irrationals and 1 for all rational numbers. That's what I have loosely depicted there. That function wouldn't be differentiable anywhere. And then there's also a function called the Weierstrass function. It's really spiky. It's basically, imagine you had a spike everywhere. I don't know, like it's really hard to picture, but that function is continuous everywhere, right? It'll draw without lifting your pen, but you won't be able to take a derivative anywhere. So really nasty function. Okay, that's probably a little too far into the theory. The real thing to remember here is corners cause problems for derivatives, and vertical tangents cause problems for derivatives. All right. Actually, I have one more theorem to write down. And then we'll be done with this video. This is what I get for putting 2 pages of notes together, or rather notes on 2 lessons together, because I'm like, oh, we're done, and then we're not. Here, if a function f is differentiable, at x equals a, that is, if f prime of a exists, doesn't matter what it's equal to, as long as it exists, then f is continuous at a. Now, here's a continuous function where the derivative doesn't exist at that point. So, continuity is weaker than differentiability. Differentiability is stronger than continuity. Alright, that's all for this lesson. Have a great rest of your day.